In the final part of this lecture, I'm going to look at magnetically ordered materials. So we've previously discussed ferromagnetism, and just to summarize this, this is a spontaneous magnetization that we'd see in a solid below a certain temperature, which we call the Curie temperature. Now, above the Curie temperature, the material is paramagnetic. It would obey the Curie-Weiss law. Okay, so in the ferromagnetic regime below the Curie temperature, we've got a positive susceptibility, but it's typically very large. Okay, so the field inside can be really quite strong in these materials, and it's also not a unique number. As we saw with the hysteresis curve, it's very dependent on what field we apply and also the history, the magnetic history of the material. So susceptibility is not uniquely defined. So what sort of materials are we looking at? Well, we've discussed insulators. So when we did the Curie-Weiss derivation, we assumed we had localized atomic moments. Now, interestingly, the most common examples of ferromagnets are actually metallic systems, okay? So iron, nickel, and cobalt, okay? They behave exactly like these localized atomic moments we talked about in the Curie-Weiss picture, but that's not a particularly good model, okay, to think about these materials because they're metallic and they've got delocalized electrons. So in the final lecture, we'll look more about how to deal with the magnetism of metals, and we'll look more on the ferromagnetism of iron, nickel, and cobalt. But to a large extent, they behave exactly like we've talked about. Domains, all of that properties are still the same. It's just that they kind of have non-integer numbers of spins. Okay. So it's a non-integer number of electrons that are giving rise to the magnetic moments, and we'll see how that arises in the next lecture. Okay, so we've got iron, nickel, and cobalt. Okay, so where are the insulating ferromagnets? And the truth is, there aren't very many. One of pretty much the first to be discovered was europium oxide. Now, this is quite an exotic material. I'm going to show you the original paper from the literature when this was discovered, so 1961. So here we have Physical Review Letters, one of the top physics journals, September 1961. And we've got collaboration between Bell Labs. So Bell Labs, Bell Telephone Laboratories in New Jersey in the US, industrial lab, but produced a huge amount of really important pure science. So there's a collaboration between two people there, and Van Vleck, who was at Harvard. Van Vleck was one of the main people working on the theory of magnetism in the early part of the 20th century, and a few years after this, he went on to win the Nobel Prize for some of that work. This is quite a short paper, and I'll give you the link because I think it's well worth a read. You can understand pretty much everything that's in this paper from the course that we have. So if I just look at the first paragraph, we have found that europium oxide of the formula europium EuO, okay, becomes truly ferromagnetic at 77 Kelvin. Okay, so its Curie temperature is 77 Kelvin. So this is a ferromagnet only at pretty low temperatures. And its saturation moment is close to 7 Bohr magnetons. Okay, it says this is thus the first rare earth oxide found to become ferromagnetic. And with the exception of chromium oxide, the only oxide in our knowledge to have true ferromagnetic coupling. So it's suggesting that actually ferromagnetism is quite rare. So let's have a look. So what have they done? So here's they've done some experimental measurements. So they're plotting 1 over chi versus the temperature in Kelvin. And this obeys very nicely the Curie-Weiss law. Okay, we've got a series of data points here, and the intersection down at the bottom there is giving us the Curie temperature. So it's paramagnetic above 77 Kelvin. That's where these data points come. And they fitted a line to this, and they've determined that the effective magnetization is just a little bit less than 8 Bohr magnetons. Okay. All right, so let's look at the next page. Okay, here's the second, it's just a very short paper, 2 pages. Now this is a graph where they've measured the ferromagnetic regime. So now they've measured the magnetization per mole as a function of temperature, and you see that this is the extrapolation down to 77 Kelvin. This is paramagnetic to the right hand side of this, and you can see very much like we predicted earlier with the spin half model, the magnetization. So you get the saturation magnetization at 0 Kelvin, and as you warm the material up, the net magnetization of the sample decreases, and then obviously at the Curie temperature it goes away completely. Okay. Okay, there's another paragraph here. The measurements are of interest as furnishing one of the clearest examples of exchange interaction in a material in which the atomic orbitals are substantially the same as for the free ions, as this is always the case for 4f electrons. Okay, what that's basically saying is that the value of the magnetic moment they found from the europium ion in this sample is the same as predicted by Hund's rules that we would have been able to calculate, and that its ferromagnetic exchange, it's the exchange interaction that is causing the ferromagnetism. Now, interestingly, they say we will not attempt to enter into the question of the precise mechanism responsible for the ferromagnetic exchange coupling. Okay, so they're saying, well, that we know it's there, but it's a little bit hard for us to work out what it is just based on the experiments that we have. Okay, so worth a quick scan through because this has some of the. I think this is quite a very simple and clear example of the behavior of a ferromagnetic material. So I think at this point you might feel a little bit cheated because we've spent quite a while developing Curie Weiss, looking at ferromagnetism, and now I've just told you that the typical ferromagnets that you know, iron, nickel and cobalt, are not actually Curie Weiss like materials, and in fact ferromagnetism is a really rare thing. Okay, we've got this quite exotic europium oxide that it becomes a ferromagnet at 77 Kelvin, but actually there aren't very many ferromagnets at all. But we know there are a lot of magnetic materials, so what are they? Okay, I just want to look at what is actually the oldest ferromagnetic material. Sorry, I should say the oldest known magnetic material. Okay, because if we look back in history, it was known from ancient times that samples of a material called lodestone were magnetic. Okay, so what is lodestone? Well, it has this formula, Fe3O4. Okay, and we know this more properly as magnetite. So this is also lodestone. We know this is a magnet. Now, it's actually a better way of writing its formula is actually FeO dot Fe2O3. Okay, now the reason for that is because the ion exists in 2 different oxidation states in this material because of the crystal structure. So this first ion here is actually Fe2+, and these ions here are Fe3+. Now, if we went and did Hund's rules on these, okay, they're 3D transition metals, so the orbital angular momentum is quenched, we've only got S, so this state is S is 2, and that would give us 4 Bohr magnetons, and this state is 5/2, and that would give us 5 μb. So we would think that the total would be 14 μb per unit cell. But if you make a measurement, say you look at the saturation, magnetization and magnetite, that's not the case. What you actually find in experiment is about 4.1 µb, so it's much less. So what is actually going on here? Well, it turns out that if you look at the Fe3+ ion atoms, their magnetic moments are arranged like this. Okay, so they're anti-parallel. So what that means is there's a negative exchange coupling. So something is driving these magnetic moments to anti-align, whereas the Fe2+ ones will be aligned. Okay, and so you can see that if these ones, if one of these contributes 5 µb, well, per unit cell, they're going to cancel out. So what am I going to be left with? Just one of those, one of the Fe2+, and that will give me roughly 4 µb, and that accords very well with experiment. Okay. So the same underlying physics can be going on that we talked about in terms of sort of Curie-Weiss, except we've now got, because of the crystallography, we've got a number of different sites, and we can have both anti-parallel ordering if the exchange coupling is negative, and as well as parallel coupling for a positive exchange. So this is, in a sense, a much more general phenomena. Okay, so here's an example. So what we have is some sort of ordering of the materials of the magnetic moments in general. There might be aligned anti-parallel, for example, but they could have different magnitudes. Okay. So actually, these compounds, the ferrites. So magnetite is just one example of a ferrite. That's one very typical class of ferrimagnetic materials. Okay. Now, its properties are really very similar to a ferromagnet. It's a permanent magnet. We have domains. All of the same things. Apply. How would you tell the difference? Well, very difficult just on the basis of, say, making susceptibility measurements. What you'd have to do is understand the crystal structure of the material, and you'd have to decide on the magnetic moments of the ions and decide whether the magnetic moments are parallel or anti-parallel. So if they're all aligned up in the same way, then we've got a ferromagnet. If they're of different sizes, potentially arranged in different orders, that will give you a ferrimagnet. Okay. So you can see now why ferromagnetism is quite rare, because there aren't that many crystal structures which are very, very simple. There are far more sort of complicated crystal structures, and so ferromagnetism is a much more common phenomena. And in fact, when you played with, if you're at school, you had some magnets, they were more likely to be ferrite magnets, so they were more likely to be ferrimagnets than ferromagnets. Now, there's one other class of material that we should just look at, and again, this is now another sort of special case of a ferrimagnet, and that's the antiferromagnet. So antiferromagnets are not magnetic materials. They're not permanent magnetic materials, I should say. Okay, so they behave, their susceptibility be above a certain temperature. They behave as a paramagnetic material. Okay, so this is behavior here, and then there is some magnetic phase transition. We tend to call this the Néel temperature, after Néel, who was the first to investigate these materials. And we find that the susceptibility is well defined, but decreases below the Néel temperature. And so what's actually happening there is we've got spins that are perfectly anti-aligned like this. So this is what we call antiferromagnetic coupling. And so if this is all that's going on in the material, there'll be no net magnetism in the material. Okay, so these materials do not form permanent magnets. And there's a variety of oxides that can exhibit this behavior. How were these discovered? Well, there's something interesting here. So what I'm trying to draw here is the unit cell of, say, manganese oxide, and I'm only going to draw in the manganese atoms. Okay. So let's imagine it looks something like this: a face-centered, simple face-centered cubic cell. Okay. Oops. Here we go. Now that is the chemical unit cell because each of these manganese atoms is identical. But if it's if these are coupled antiferromagnetically, it means that, say, this one is magnetic moment up, these will be magnetic moment down. Okay, so what I've drawn here is a much larger. So this is my unit cell. That's my chemical unit cell here. Okay, but that now is no longer the actual unit cell because this atom and this atom are not identical because their magnetic moments point in opposite directions. I have to make a supercell. I have to make something that's twice as big in each direction. So this would be my magnetic unit cell. Now, the thing that's interesting is if you do X-ray diffraction, X-rays scatter off the charge density. So the X-rays would measure this unit cell. But if you did neutron diffraction, so you're using neutrons to scatter, they don't scatter off charge because they're neutral. They scatter off magnetic moment. Okay. So from the point of view of neutron diffraction, they would see this twice as big unit cell. So the diffraction pattern that you would get from X-rays and neutrons would be different. It would have twice the spacing. Okay, that would be completely different to say something if you did a silicon unit cell, for example, something that was non-magnetic. You would find that the unit cell from X-ray and the unit cell from neutron diffraction would be identical. Okay. So antiferromagnets we find obey a modified Curie-Weiss behavior. Okay, so it looks something like this, where we end up with a plus sign here instead of the minus sign, and that's because the molecular field constant, okay, the Weiss field is negative, so that's driving the spins, the magnetic moments, to anti-align in this way. So that is itself quite useful because if we were to one way to distinguish between these materials is to look at a graph of one of the susceptibility versus temperature, where this is measured in the above the ordering temperature, so in the paramagnetic regime. And for the antiferromagnet, we would find a straight line, okay, up until the Néel temperature. But if we were to then intersect that line back, okay, we find that it would intersect at a negative temperature here, where this intersection here, theta, is approximately the same as the Néel temperature. Okay. Whereas for both the ferromagnet and the ferrimagnet, we would find that the susceptibility diverges. Okay, so 1 over the susceptibility goes to 0 at the Curie temperature. Okay, so this is the way that we can quite easily, for the basis of susceptibility measurements, differentiate between the antiferromagnet and the ferro or ferrimagnet. But this type of measurement does not distinguish between ferro and ferrimagnet. As I said, to distinguish between those, you have to really consider the crystal structure and the magnetic moments and make a decision as to what's happening about the actual magnetic ordering.